Red Bull just launched their new RB22, and while the car shown in person was just an F1 show car, the car in renders looks quite different. And in this video, we're going to go from the front to the back, analyzing all the aerodynamic features on this car. For those of you that are new to my channel, I was an aerodynamicist for Mercedes for the 2018, 19, and 20 Formula One seasons. I now work as an aerodynamics consultant, designing packages for race cars and OEMs in all different classes all around the world. Now this video of course comes with my standard disclaimer that no aerodynamicist can perfectly predict all flows by eye, so everything presented in this video is at best an educated guess. Now while it's unlikely that the car that we see here is the exact final specification that we're going to see at race 1 or even testing, it's clearly some evolution of the development that may have been from quite a bit earlier on in the process. So anyway, we're going to analyze it as if it's real, and then if a new one comes out, well, you can always get another video. Okay, so starting at the front end. Now, this is our first look at a 2026 F1 front wing, and there's a few interesting details on this one. The first one I draw your attention to is just this little strut that we see in the center down here. Now, given the rules on the front wing pylons, where basically those have to be in this space here, in different boxes there, I'm going to guess that what's in the center is the front active aero adjuster. It's also interesting to note that on the RB that was launched at the same time, it had two very clear adjusters here and here. Looking further to the outboard, what we can see is that we have a vertical fin along here, as well as a curled footplate. Now the curled footplate, I think everyone knew was going to be the case. The vertical fin, I thought, may or may not have existed depending on how teams wanted to use the regs there. The way it works is that basically you're allowed to have two sections within a Z-plane in this region. They've obviously just gone and made it so that when you slice through, they've got one section here and then another section over here at the front. Because when I show you from the side, you'll see that it's monotonically going downhill as we go along this footplate here. Now, looking at the wing itself, what you'll see is that the front wing end plates appear to be canted inwards. So from top down, they're sweeping in an inwashing manner, but they also seem to have the top edge pulled this way towards the inboard. Now, what does this mean? Well, on a wing like this, you'll have high pressure on the top and low pressure on the bottom, but generally speaking, it also means you have relatively low pressure here compared to the inboard side of the wing. Now, these rules force us to have an outboard loaded wing. They have a rules box that looks something like this. So we have to have a wing that ramps up towards the outboard side. So this will naturally cause a vortex that is trying to spill over the top of the end plate in that way. So it'll be rotating that way as it goes downstream. Now, with this particular end plate and vortex trajectory, you want to try and make sure that you are not going to just slap into the front face of the tire if you want to use that vortex for downstream management. Now, there is an exception to this, which is, of course, if you have a vortex up here that's, say, outwashing the tire and you want it to run over the tire, you can outwash the upper wheel wake with that. But if you don't have that feature and the rules restrict you to a certain positioning of the front wing end plate, which they do in this case, we obviously can't run that trick. Now, with all of this in mind, basically, what Red Bull is doing here is they are trying to guide that vortex further inboard by moving that top tip inboard, and they're also powering it up by making the front wing end plate inwashing. Now, why would you want to do this? Well, if you have a vortex that is rotating in this direction downstream and is quite powerful, it's downwashing onto the tire. So as it's going along, it will be pushing down the upper wheel wake over the back of the tire as it goes downstream. So this could potentially help with suppressing some of the upper tire wake. Now, it's a bit hard to work out if it's actually going to go high enough for that to be a thing. Obviously, you have to balance two things here. One is the upwash from the front wing. The other one is the fact that the top edge of the front wing end plate is relatively low. So the upwash will naturally cause the vortex to drift upwards, but the starting position being low will keep it low. So in terms of trajectory, maybe it's hitting the front wishbone, maybe it's going higher up. It's a bit hard to tell. But where it's placed would change what you're specifically looking for in that vortex. All of these things come with trade-offs because obviously the more rotation you have in that, the more outwash you get further rearwards, lower down, which makes your mid-wake a little bit harder to control. Looking from this top-down view, you can see even clearer that inwash. So basically what you've got those front wing end plates curving inboard, and you can see that that's going to position it inside of the tire. Now, this also has ramifications with respect to how the lower portion of the end plate is loaded, where if you in-wash the end plate down low, what's going to happen is you're going to reduce the amount of expansion under the wing in this region. So you're going to depower that part of the wing, and you're going to weaken any vorticity that may be forming off the lower edge of that end plate down the bottom in the cone region. Now, sometimes that can be beneficial in terms of weakening that can clean it up, but also the position of that particular structure is likely important on these cars. The bulk of the cone vortex is probably going to be sitting on a trajectory somewhere around here, and I imagine how they guide that through this region here is going to affect how it draws in the lower tire wake a lot, and probably some of the flow features of the forward floor. You can also see in this shot that little vein I was talking about on the top of the outboard front wing end plate, just there. So that particular vein, for clarity, is just this bit here, and you see that that is very clearly inwashing. Now, being that inwashing nature, it will be rotating a vortex in the same direction as the front wing end plate top trim vortex. And that vorticity, looking at that, is going to be pretty close to impacting on the front of the tire. And that means that the direction it goes will be a little bit dependent on the overall bulk flows here. Now, I'm going to say that with a fairly strong top trim vortex plus an inwashing direction of this structure here, combined with the high pressure on the front of the tire, my guess at this would be that it would be going to the inboard side of the tire. But some of these things all rotate around each other here, and things can go in kind of weird places. One of the other interactions that it might be pairing up with is the vortex coming off this canard here. And let me show you that from a different angle. You can see that the canard here is very heavily cranked towards the rear. It also, as you'll remember from the top view, flares out laterally quite a lot. So they've really powered this up quite hard. They're trying to get a lot of load out of that. So obviously it will create local load and a little bit of downforce, but it's mainly going to be increasing the strength of the structure that is spooled up off the edge and heads downstream. Now, a few different interactions are going on here. You have the top trim vortex, which, like we discussed, is spinning that away. That's going to try and draw in this canard structure that way. We've then got this bottom bit here, which is inwashing as well, but it's going to be trying to rotate and push that canard vortex outboard. Now, I would imagine if you got the positioning right and the strength right, you could get this vortex to go to the outboard side of the tire. And that may have some benefits in terms of managing the outer tire wake, which, whilst usually not as influential as the inboard tire wake, it can have some adverse effects further downstream. And with the lack of complex and effective forward floor devices, particularly those to generate outwash, maybe this is a more important structure than it used to be. Moving further downstream, we have the front Caketin. These Caketins on this car give us the first real look at the front Caketin deflector, which I'll show in another shot. But one thing I wanted to show you was the front Caketin lip geometry that they've used on here. What you can see is that they've gone and made a lip that comes over the top and then has a free shedding edge at the top. Now, why do they do that? Well, having that geometry creates pressure near the tire, so you help with any separations around the shoulder of the tire, but that's just any lip geometry. But having this free shedding edge means that we get that pressure differential around a tip and we spool up a vortex in this direction. The presence of this vortex can help with separations and losses off the tire sidewall shoulder just here, because you've got to remember the tire at this point is traveling forwards, so the boundary layer losses on it can be quite substantial. So adding a bit of vorticity there can help suppress that. And also you can use it to generate outwash down rearwards, low down. So it continues to outwash this part of the tire wake out here, and that can help with performance of the floor further downstream. Looking here at the front Caketin, you'll see that the scoop is relatively simple, nothing too fancy to talk about, apart from the fact that the intersection with the lower wishbone looks like it might be a little bit nasty from a loss perspective. But we do get to see a bit of that front Caketin deflector showing there. That's an FIA standard part that's being added that for some reason outwashes the lower wake. I'm going to assume that that's a performance related thing. I mean, we normally would try to outwash the lower wake. It just seems against their usual intent of trying to improve the performance of a following car, where you'd think that any outwash you add here, generally speaking, would tend to kick the whole lower wheel wake outboards a bit, and I wouldn't have thought that would be necessarily in line with their intent, but they do still have to make these cars have some level of performance. You'll also note that this is a pushrod front suspension. This car is pushrod front and rear, and Why push rod versus, say, pull rod, which we've been seeing show up recently? Well, I mean, I've gone through the mechanical reasons of push rod versus pull rod many a time in previous videos, so I won't go through again. But aerodynamically, maybe it's a case of, in this set of rules, having this scoop low and the Caketin clean higher up, where you can use that top deflector that we spoke about earlier, might be a better strategy, in which case you want to move the scoop down, and if the scoop's down, you're lossy and messy down here anyway, you might as well put all the suspension geometry in this region. That's just some speculation on why they might have wanted to move the scoop low and to push rod for this car. From this forward view, you can also see the floor leading edge just here. You can see they've used that full delta wing available in the box. There is a bit of box room here that allows you to put a delta shaped leading edge on the floor, and they've really run that up to the full size of it. Now, that particular detail will, generally speaking, produce high pressure above it, and that will cause a degree of vorticity to be spun up on the edge because there'll be suction underneath and high pressure above. And this should be fed to the floor. I've drawn it a little bit further outboard than it realistically would be in here. Usually when it gets under the floor, it sort of tracks a bit more along the center line and sort of sits housed in the area between the drop down in the center of the car where the plank is and the step plane. This was a pretty common detail back in the 2 generations ago cars. You can also see the smallest indications of the floor leading edge daggers just on the sides. We don't have a great shot of those, so we really can't see what the geometry is yet. We have a much better shot on the RB, but not so much on this car. Moving further rearwards, you can see the floorboard here. Now, this is a geometry that a lot of people had kind of predicted would come out as the season went. There were some DIY cars running around that had this geometry already, so the geometry is not a particular surprise. But the things that I think are quite noteworthy on this is that looking at the size and height of this floorboard and comparing that to my reference volumes and surfaces, it looks to me like they're almost at the minimum height and size they can be on this floorboard. So they tried to reduce the volume as much as possible, which is presumably to allow more natural outwash from the stagnation pressure that's captured by the Sidepod, and we'll talk about the Sidepod in a little bit. And it will be interesting to see whether teams go for this minimalist approach or try to go for a bigger filling of the regs boxes. Now, this particular geometry is made up of a vertical element here that does the initial turning. Then you have 3 horizontal elements. These elements are upwashing elements. So basically, as the air comes along through from the center line of the car, it gets turned sideways by the stagnation on the Sidepod. And then it comes out here. There's a lot of pressure on the inboard side of this board, and then it gets upwashed by those vanes. Now, that upwash will produce local load on the board through here, rather than just trying to turn it dead rearwards. It was very common in what we did on 2 generations cars ago. And how much they choose to crank this upwash or increase the openings in this region, which we call the porosity, would change how the balance of pressure on the inboard side versus the outboard side is looking. And that balance of pressure will change how your front tire wake is behaving, and also how much your floor leading edge is pressurized. And not just your floor leading edge in the center line, but you can see that there's a little foot below this board along here, and that is going to be locally pressurized by that. And the upwash from these elements would actually help with extraction from the floor here, because you're creating a large amount of upwash, you're pulling out there, that creates suction under the floor, which then proceeds to drive the entire floor system harder. So this is why this type of geometry can be quite beneficial. What's interesting though on this model is that they don't seem to have used any sort of curl further rearwards to get even more extraction in that region. And I wonder if that's a detail that we're going to see more and more cars start to show up with as we get closer to test and race. Looking at the top shape of this board is actually quite funky too. You can see, like I was mentioning, we've got that big foot beneath it, and it looks like they've maxed out a lot of the volume there to try and maximize the amount of pressurization on the top surface there. So really increase that local load. And if there's any suction underneath, improve the power of the suction in this box the whole way and get communication to the forward floor. But the thing that draws my eye is the shape of the board overall. You can see that the first element is fairly outwards aligned. Now, we've got to be careful here with calling these elements outwashing or inwashing. There's naturally going to be a tendency for the air to outwash there by itself because of the presence of the pressurization here. So sometimes an element that looks like it's angled out can still, technically speaking, be an inwashing element, because if you removed it, there'd be more outwash. So I can't be certain on which direction this is, although looking at the profile, it looks pretty neutral to me. It doesn't look like there's a huge amount of either inwash or outwash on that particular profile. But then if you have a look, the elements themselves have this kind of sweep to them. They kind of go in, then out again, and then they come back in as they taper down to their edges. Now, if I had to guess what they're doing here, I would say that they're trying to get that leading edge a little bit more aligned to the local flow direction. Maybe there's a little bit more axial flow here, and then a little bit more lateral flow in this region here. It's very subtle alignment that they're doing here, but they're only allowed subtle things within the rules. But that would be my guess if I had to say that something was going on here. Now, for a short bit of shameless self-promotion, did you know that I also do aerodynamics courses? I've got a FlowViz course and a race car aerodynamics course that's been around for a few years now. People generally seem to love it. We've had a number of university students that have used it to get into Formula One, and there's been a bunch of race teams that have made their cars faster with it. The courses are ideal for university students, amateur racing teams, and professionals looking to upskill more into aerodynamics. For more details, you can go over to courses.jkfaero.com. Now, the Sidepod leading edge geometry is really nothing different to what we've seen in the previous year's rules. I suggest you go back and have a look at my previous year's Red Bull analysis if you want to work out how that's going. Basically, this whole front section from here forward seems to be the previous one. Now, like I mentioned earlier, this is very likely an early development model that we're getting shown. This isn't probably the final model of the car. It would make natural and logical sense for the team to start their bodywork development with the bodywork that they've previously run, just to save a bit of resource and then come up with new concepts from there. So this could just be what they ran earlier on in the development cycle. Further rearwards though, you'll notice that we have the same sort of downwash as we had last year, but there's now a lot more lateral taper on the bodywork. So it's really falling away in all directions, which is a little bit closer to what was being run again 2 generations ago. And I'm making a lot of these comparisons to cars 2 generations ago, and there's a lot to be said about these cars have a lot more similarities to those cars than last year's cars with respect to the floor geometry having a step plane, with respect to having some freedom in slotting the outboard edge of the floor, having the splef type region down here. Things like that are a lot more similar to 2 generations ago than current. Looking a bit higher up, you'll see that we've got these 2 halo winglets along here. Those are to control the cockpit losses usually. So there's going to be some degree of loss spilling out of the cockpit. There's going to be some vorticity shed off this particular winglet. There's likely to be more pressure on the inside than the outside if I had to take a guess. And so they will try and hold those losses a little bit more in and control how they go downstream. Things like this are usually fairly marginal gains. In terms of other detailing up here, the wing mirror looks fairly vanilla, nothing too spicy going on there. Looking a bit further back, you'll see that we have a panel here, a little patch panel for adding additional cooling through there. That's obviously where they've deemed to be the most effective region for cooling losses at the moment, and any losses from this area that come out will spill flow along here and should pass somewhere around here. Remembering that the beam wing doesn't exist anymore, it's just a little stay on the main wing now, so putting your losses a tiny bit lower down might be a little bit easier to tolerate than it was in the previous generation of cars. And you'll see that there's a lot of downwash on that rear engine cover at the back. There's a lot of downwash going on there, which would be loading the rear wing and would also be consistent with what I was just discussing about the beam wing effectiveness being diminished. Down to the outside here, you'll see that we have a number of slots in the floor, and I'll just show you those from the top view. So you can see these slots just here, and they've got some degree of freedom in this particular region on this rule set. So you can see we've got slots along there. Again, 2 generations ago, very similar design. And these slots basically allow you to bleed in clean mass flow that's above the floor into the area under the floor. And you can spool up little vortices on the edges of the slots. So it allows you to put some vorticity inboard, where normally the vorticity would just build up on the outboard edge, but you can use these slots to put the vorticity inboard. And it's quite clean because you're bleeding in clean mass flow from above. And that vorticity usually goes alongside the tire, and use that to control your tire wakes, your squirt, etc. Obviously, the game is a little bit different this year with how they're restricting the Caketin winglets and the little winglet that sits on the side of the diffuser. But my guess would be there's still substantial benefit to managing this area effectively. A little bit further back, and you can see that we've got another one of those details on the Caketin just here. Another one of those little flicks on the front lip, much like I spoke about on the front Caketin. It's also worth observing here that you can see that taper in the lateral direction that I was talking about with the bodywork, where you really have that tapering in there like that. Now, the final thing to talk about, because we can't really talk about the diffuser because it's kind of hard to see, but basically we have ourselves our first 3-element rear wing. Now, the thing that is so interesting to me about this rear wing is the distribution of the elements. But what they've done is they've gone for one very long first element and then 2 shorter second elements like that. So it's not an even distribution of rear wing elements, which was always shown in the concept models and frankly never really made a whole lot of sense for the active aero system. This is the first time that we're getting to see a far more realistic indication of what the rear wing is. If you look at it from here, what you can see is the last 2 elements are relatively cranked, while the first element is actually quite flat through there. So that first element is going to be very flat, which is going to mean that because whenever you're driving around on a straight, the active aero system is going to be just open like that, you're going to have minimal drag and minimal power on this wing, which is exactly what you want when that active aero system is open. This year, they're allowed to open the active aero system on every straight, so it completely changes the game with how you design the rear wing, because you don't need to worry about efficiency when it's closed. You just try to design the wing so it makes maximum downforce when the wing is closed, and then when it opens, it makes minimum drag. So it makes sense that one long flat section and then a heavily cranked rear section with 2 elements to make sure that it can accept what's probably a very peaky alignment on the first element in order to get it to get the best performance when it's open. And I wouldn't be surprised if we see strategies similar to this across the grid. The other thing that's interesting as well is the lack of rear wing end plate notch. There's a very tiny dip down in the rear bit there, not a whole lot, it's really small. And I wonder if that's a consequence of just this rear wing this year is a lot more depowered, it's a much smaller box, and you don't have to worry at all about the efficiency when you have the wing closed, like I previously mentioned. So maybe just going in and filling that whole area in is the most powerful way of increasing the oomph out of this rear wing. The rear wing end plates from this generation are certainly a lot simpler than the ones that I used to work with. So there's probably a lot less you can do in terms of the vortex interaction of the forward vortex and the suction of that in the rearwards portion. But I'm sure we'll get to see some different interpretations from the teams as the launches progress. You'll also note that at the rear, we have a push rod set up here. I would hazard a guess that with the new rule set, even though the floor is not quite as big, there's probably still enough diffuser volume to justify going to push rod here instead of going for pull rod. And that is my analysis of the Red Bull RB22. Well, that's all for this analysis video. If you liked it, don't forget to hit that like button and subscribe to the channel, as well as turning notifications to on so that you get pinged whenever I happen to upload a video. Leave a comment below on what videos you'd like to see next from me, and hopefully, I'll see you next time.